Distance matters in cometary science. Approach the sun, temperatures rise, ices sublimate, activity begins. Move farther away, temperatures drop, sublimation ceases, comets go dormant. This relationship between solar distance and activity has governed our understanding for centuries. Predictable, quantifiable, reliable. 3. iAtlas is ignoring it. This interstellar visitor is showing sustained activity at solar distances where conventional models predict silence, where water ice should remain frozen solid, where typical comets show no coma, no tail, no detectable outgassing. Yet 3 iAtlas continues releasing material, continues brightening, continues behaving as if it's much closer to the sun than it actually is. This isn't marginal deviation. This isn't activity barely above detection threshold that might be explained by measurement uncertainty. This is clear, sustained, measurable activity occurring hundreds of millions of kilometers farther from the sun than water ice sublimation models can explain. Observatories tracking the comet as it recedes from perihelion expected to see activity decline following standard thermal curves. Brightness should fade predictably. Gas production should drop. The coma should shrink. All following equations derived from studying thousands of solar system comets. Those expectations are failing. 3. iAtlas remains more active than predictions indicate it should be at its current distance. The discrepancy grows as the comet moves farther outward. Something is driving continued outgassing that doesn't match water-dominated composition models. The implications extend beyond one unusual object. If interstellar comets routinely show activity patterns that don't match solar system norms, our models need fundamental revision. Not tweaking, not adjusting parameters. Reconsidering basic assumptions about what drives cometary activity and how composition varies across different stellar environments. This is the story of a comet that won't follow the rules. That continues surprising observers with each new measurement. That's forcing scientists to acknowledge that their understanding, comprehensive as it seems for local objects, doesn't generalize to visitors from beyond. Understanding why 3 iAtlas behavior is anomalous requires understanding how cometary activity normally works and at what distances. Water ice, the dominant volatile in most solar system comets, has well-characterized sublimation properties. At the vacuum pressures of space, water ice begins sublimating significantly when surface temperatures exceed approximately 190 Kelvin, about negative 83 Celsius. Below that temperature, sublimation is negligible. Solar distance determines surface temperature through straightforward physics. Solar radiation intensity decreases with the square of distance. At 1 astronomical unit, Earth's distance, a dark surface in vacuum, reaches temperatures around 390 Kelvin. At 2 astronomical units, that drops to about 276 Kelvin. At 3 astronomical units, around 225 Kelvin. These temperatures depend on surface properties. Darker surfaces absorb more radiation and heat more. Brighter surfaces reflect more and stay cooler. But the basic scaling with distance is unavoidable. Farther from the sun means cooler surfaces. For water-dominated comets, significant activity begins around 2 to 2.5 astronomical units from the sunday, closer than that. Water sublimation drives vigorous outgassing. Farther than that, water remains mostly frozen and activity drops to low levels or ceases entirely. 3 iAtlas is currently beyond 3 astronomical units and receding. At this distance, water ice should be largely dormant. Some residual sublimation might occur from the warmest surface regions, but bulk water activity should have dropped dramatically from perihelion levels. Yet observations show continued substantial activity. The coma remains prominent. Brightness exceeds predictions for a water-dominated comet at this distance. Spectroscopic signatures indicate ongoing gas release at rates inconsistent with minimal water sublimation. This distance activity mismatch is the core anomaly. 3. I-Atlas is active where it shouldn't be, implying either that something other than water is driving the outgassing, or that the comet has properties that make standard thermal models inadequate. Subscribe now, because understanding what's powering 3I Atlas at these distances might reveal composition fundamentally different from any comet we've studied before. The leading explanation for unexpected activity at large solar distances is hypervolatile ices. These are compounds that sublimate at much lower temperatures than water, remaining active when water freezes. Carbon dioxide is the most common hypervolatile in solar system comets. It sublimates significantly at temperatures around 145 Kelvin, negative 128 Celsius. At 3 astronomical units, surface temperatures in the low 200s Kelvin are sufficient for vigorous carbon dioxide sublimation, even though water remains largely frozen. If 3I Atlas is carbon dioxide rich rather than water rich, continued activity at current distances becomes explainable. Carbon dioxide would continue sublimating vigorously, driving outgassing, releasing dust, maintaining the coma, keeping brightness elevated. All the observed activity could be carbon dioxide driven without requiring water sublimation. Carbon monoxide is even more volatile, sublimating at around 68 Kelvin, negative 205 Celsius. At typical cometary distances, carbon monoxide sublimates freely. If present in large quantities, it could drive activity at enormous solar distances where both water and carbon dioxide remain frozen. Other candidates include methane, nitrogen, and ammonia. Each sublimates at different temperatures. A comet with the right mixture of these hypervolatiles could show sustained activity far beyond where water-dominated objects go dormant. Spectroscopic evidence supports this hypothesis. The transient blue coloration observed during perihelion indicated carbon monoxide or carbon-bearing radicals. Preliminary analysis suggested elevated carbon dioxide abundance. If confirmed, these observations directly support hypervolatile dominance. But hypervolatile composition alone might not fully explain the observations. The activity level at 3I Atlas current distance seems high even for carbon dioxide. Either the carbon dioxide content is exceptionally abundant, or multiple volatile species are contributing, or additional factors like unusual structure are amplifying the outgas. Composition isn't the only factor affecting activity patterns. Internal structure profoundly influences how solar heating drives sublimation and how efficiently gas escapes from the interior. A porous, rubble pile structure allows heat to penetrate deeper than in cohesive nuclei. Solar radiation absorbed at the surface conducts inward through the material. In porous structures with high void fractions, heat reaches subsurface ice deposits faster. This accelerates sublimation of buried volatiles that wouldn't be heated as quickly in denser structures. If 3I Atlas has exceptionally high porosity, solar heating might activate volatile deposits throughout a significant fraction of the nucleus volume rather than just surface layers. This would increase total gas production beyond what surface-only sublimation would provide, maintaining higher activity at larger distances. Fractures and internal pathways also matter. If the nucleus contains cracks and fissures connecting deep interior to surface, gas generated from subsurface sublimation can escape efficiently. In contrast, a cohesive structure without pathways would trap subsurface gas, allowing pressure to build but preventing efficient release. 3I Atlas might have acquired enhanced porosity or fracturing during its millions of years in interstellar space. Thermal cycling, as it occasionally passed near stars, radiation damage from cosmic rays, or inherent structural weakness from formation could all contribute to creating a highly fractured, porous interior that responds to solar heating more dramatically than typical solar system comets. This structural amplification could work synergistically with hypervolatile composition. Carbon dioxide sublimating throughout a porous interior, escaping through extensive fracture networks, could produce activity levels at large distances that pure surface sublimation couldn't match. Comment below. Do you think 3I Atlas high activity comes primarily from unusual composition or unusual structure? 3I Atlas represents the third data point in our growing catalog of interstellar objects. Comparing its activity pattern to previous visitors highlights how unusual it is. 1I Oumuamua showed no detectable cometary activity throughout its solar system passage. No coma formed, no tail developed, no spectroscopic evidence of sublimating volatiles appeared. Whatever its composition, either volatiles weren't present in substantial amounts, or conditions during passage didn't trigger their sublimation, or outgassing occurred but was too weak to detect. Oumuamua's inactivity sparked intense debate because slight non-gravitational acceleration was detected despite the absence of visible activity. Explanations range from outgassing of invisible volatiles like hydrogen to exotic hypotheses. The mystery remains unresolved. 2I Borisov displayed conventional cometary behavior. Water vapor dominated its composition. Activity onset, brightness evolution, and spectroscopic signatures all matched patterns observed in solar system comets. Borisov demonstrated that some interstellar comets form through processes similar to local comet formation, producing objects with familiar properties. 3I Atlas occupies middle ground but with a twist. It shows clear activity like Borisov, unlike inactive Oumuamua, but its activity pattern doesn't match conventional behavior. The sustained high activity at large distances, the spectroscopic hints of unusual composition, the brightness evolution that exceeds water ice predictions all distinguish it from conventional Borisov. 3 objects, 3 distinct profiles. Oumuamua, inactive and mysterious. Borisov, active and conventional. 3I Atlas, active and anomalous. This diversity suggests interstellar objects span wide compositional and structural ranges, more varied than solar system populations might suggest. As detection rates increase, as more interstellar visitors are discovered and characterized, filling in the parameter space between these extremes will reveal the full diversity of objects formed around different stars under different conditions. Characterizing 3I Atlas distance activity relationship requires sustained observation. As it recedes from the sunday, scientists are tracking brightness, spectroscopy, and morphology to determine how activity evolves with changing solar distance. Photometry measures brightness over time. By comparing observed brightness to predictions from thermal models assuming various compositions, astronomers constrain what volatiles are actually present. If brightness follows carbon dioxide sublimation curves better than water curves, that supports hypervolatile dominance. Spectroscopy identifies which molecules are being released. Water, carbon dioxide, carbon monoxide, and other species have characteristic emission lines. Measuring relative abundances as the comet recedes reveals which volatiles remain active at various distances. Water emission should fade faster than carbon dioxide emission if carbon dioxide is more abundant. Imaging tracks coma size and morphology. The coma extent depends on gas and dust production rates. As activity declines, the coma should shrink. Measuring shrinkage rate provides another constraint on which volatiles drive activity because different species produce different coma structures. This multi-technique approach builds comprehensive understanding. No single measurement definitively determines composition, but combining brightness evolution, spectroscopic identifications, and morphological changes creates a consistent picture that favors certain compositional models over others. The challenge is that 3I Atlas is fading as it recedes. Eventually, it will drop below detection thresholds for detailed spectroscopy. The observing window is limited. Scientists must collect as much data as possible while the comet remains accessible, knowing that opportunity will end within months. If 3I Atlas activity pattern is confirmed to result from hypervolatile dominance, It has implications for how we model comets generally and interstellar comets specifically. Current cometary activity models are parameterized primarily around water ice. They include terms for other volatiles, but water dominates the energy budget and activity patterns in most cases. These models work well for solar system comets because most are indeed water-rich. But if interstellar comets routinely have different volatile ratios, applying water-dominated models produces incorrect predictions. The distance at which activity begins, the rate at which it increases approaching perihelion, the rate at which it declines after perihelion, all these depend critically on what ices are present and in what abundances. A carbon dioxide-dominated comet follows completely different thermal response curves. It becomes active farther from the sunday. It may show less dramatic perihelion brightening because carbon dioxide is already sublimating vigorously before closest approach. It maintains activity to larger distances as it recedes. Models need to accommodate this compositional diversity. Instead of assuming water dominance and treating other volatiles as perturbations, models must allow for arbitrary volatile mixtures and calculate thermal response based on the actual composition present. This isn't just academic refinement. It affects practical questions like predicting how bright interstellar comets will become, estimating when they'll be observable, planning observation campaigns, and interpreting data. Using inappropriate models leads to incorrect conclusions. 3I Atlas is teaching us that one-size-fits-all models don't work for objects from diverse stellar environments. Each interstellar visitor might require individual compositional modeling rather than assuming it resembles solar system comets. The suspected hypervolatile composition provides clues about where and how 3I Atlas formed. Volatile ratios in comets reflect conditions in the protoplanetary disk regions where they originated. In our solar system's disk, temperature decreased with distance from the young sunday close to the star. Only refractory materials remained solid. Farther out, water ice condensed. Still farther, carbon dioxide became stable. Even farther, carbon monoxide, methane, and nitrogen condensed. Comets formed in the outer disk, beyond the water ice line, but primarily in regions where water dominated over more volatile species. This produced the water-rich composition typical of solar system comets. If 3I Atlas formed around a different star, disk conditions could have been different. A lower mass, cooler star would have had a colder disk. The water ice line would be closer to the star. The regions where carbon dioxide and carbon monoxide dominated would extend over larger disk volumes. Comets forming in such a disk would naturally incorporate more hypervolatiles relative to water. They wouldn't be water-rich. They'd be carbon dioxide-rich or carbon monoxide-rich, depending on exact formation, location, and disk chemistry. Alternatively, the parent star might have had unusual chemical abundances. If the molecular cloud from which it formed was carbon-enriched relative to oxygen, the disk chemistry would favor carbon-bearing molecules over water. Comets forming there would reflect that carbon enrichment. Either scenario, colder disk or unusual chemistry, produces comets with volatile ratios different from solar system norms. 3. I-Atlas composition, if confirmed as hypervolatile rich, constrains which type of stellar environment it came from. 3I Atlas will continue being observable for months. As it recedes past 4, 5, 6 astronomical units, tracking how long activity persists will provide crucial data. If activity remains detectable to very large distances, beyond where even carbon dioxide should be largely dormant, that would suggest even more volatile species like carbon monoxide are present. Each volatile has a characteristic turn-off distance where its activity becomes negligible. By observing where 3I Atlas activity finally ceases, scientists can infer which volatiles are actually present. Spectroscopic monitoring will track molecular emission ratios. The ratio of carbon dioxide to water emission should increase with distance if carbon dioxide is more abundant because water will fade faster. Quantifying this ratio evolution provides direct compositional information. Brightness measurements will test whether decline follows predictions for carbon dioxide or whether it shows different patterns suggesting mixed volatile composition. Pure carbon dioxide should produce specific brightness curves. Deviations indicate additional species contributing. Eventually, probably within 6 months, 3I Atlas will fade below detection thresholds even for large telescopes. At that point, analysis shifts from active observation to modeling accumulated data. The complete light curve, all spectroscopic measurements, and morphological evolution will be fit with comprehensive models to determine best fit composition and structure. Those results will take time to finalize, pass peer review, and publish. But they'll provide definitive characterization of 3I Atlas composition and settle whether it truly represents a new class of hypervolatile, rich interstellar comet or whether alternative explanations better fit the complete data set. As I record this, 3I Atlas continues outbound from the Sun, continuing to release material at distances where conventional wisdom says it should be going dormant. The sustained activity challenges models that have successfully described thousands of solar system comets, but apparently don't apply to this visitor from beyond. Scientists are tracking the comet's evolution carefully, measuring brightness, analyzing spectra, monitoring how long activity persists. Each observation adds data that will eventually reveal whether hypervolatile composition, unusual structure, or combinations of factors explain the anomalous behavior. This isn't just about one unusual object. It's about recognizing that our models, comprehensive as they seem for objects we've studied extensively, might not capture the full diversity nature produces. Comets forming around different stars, under different conditions, with different chemical abundances, will naturally differ from our local population. 3. IATLAS is teaching us humility, demonstrating that predictions based on solar system experience don't necessarily apply elsewhere, showing us that the galaxy contains comets we haven't accounted for in our theories, revealing that diversity extends beyond what limited sampling of interstellar visitors has shown so far. The interstellar comet that surpasses all models continues surprising us. Each measurement that exceeds predictions is information. Each deviation from expectations is a clue about formation conditions in stellar environments we cannot directly observe. And each observation brings us closer to understanding the true variety of objects filling our galaxy. 3I Atlas won't follow our rules because it wasn't formed under conditions our rules describe. It came from somewhere else, shaped by different physics, different chemistry, different stellar environment. And by studying how it differs from what we expect, we learn what that somewhere else was like. Comment below, how many more interstellar visitors do you think we need to observe before we truly understand the diversity of comet composition? And subscribe, because 3I Atlas observations continue, models are being revised, and as scientists work to explain this comet's unexpected behavior, we'll bring you updates on what they discover about the incredible variety of objects traveling between the stars. The comet that ignores the models is still being watched. The activity continues farther than predicted. And somewhere in the sustained outgassing at impossible distances, the truth about this ancient traveler's exotic composition is revealing itself.